Hey, my name is Katharina and I'm happy to show you what my master thesis was about. First, what system are we looking at? We have a silica sphere with a diameter of around 300 nanometer that is levitated by some potential. Due to the levitation, the particle is well isolated from the environment. Regarding its size, the sphere is huge compared to microscopic objects as single atoms, but it is very small compared to macroscopic systems. So the levitated nanoparticle is a system right in between what we describe with quantum mechanics and what we describe with classical mechanics. Why is this interesting? Because we do not know a lot about that boundary. Why exactly do we have to describe our world with two different theories, and is there a certain point where quantum mechanics takes over? So in order to answer those questions, we have to bring our nanoparticle, which is in a thermal state, towards a quantum state. And the way to do this is to trap the particle, for example in a Paul trap, and to cool down the mechanical motion in the field of the trap. To obtain cooling, we observe the displacement and react by pushing it into the opposite direction, and by this reducing the amplitude of the particle's motion. So we introduce damping based on a measurement of the position. What is clear, the more precise we can measure the motion of the particle, the better we can react and feedback cool. Therefore, we have to improve our measurement technique. My master thesis was part of this improvement. Based on a theory proposal by Giovanni Cercari and others, we, that is the nanosphere team of Tracy Northup, realized a proof of principle setup to test a new position measurement for a levitated nanoparticle. To understand this improvement, let's quickly look at the former standard measurement technique. The levitated particle is illuminated with a focused laser beam. It scatters light as a dipole, and the scattered light interferes with the transferred laser light at the detector. The position of the particle is encoded in the phase of the interference pattern. This scheme has two main drawbacks. First, the wavefronts of laser and dipole radiation do not match. And second, the particle scatters light into the full solid angle, but we only collect a small percentage, so we lose scattered photons and therefore position information. The new scheme, we call it Self-homodyne, addresses both problems with the following. We illuminate the particle again with a laser, but now we introduce a spherical mirror, which reflects the light on one half of the solid angle and forms an image of the dipolar particle at a known position. This image then interferes with the particle's scattered light in the other half of the solid angle. Thus, we interfere two fields with identical properties, and we collect an amount of scattered photons that is only limited by available optics. This is the main idea. Now we transfer it into an experiment, and for real implementation, we replace the curved optics by lenses and flat optics. Here's a picture of the main setup. The details are less important. Main parts are the vacuum chamber, where we levitate the particle in a Paul trap, a movable mirror, guiding and focusing optics, and a detector. Moreover, we implement the former standard measurement scheme in the same setup. Why? Because it allows us to directly compare the old and the new technique. Let's have a look at the main results. The sensitivity of the measurement is indicated by the noise level of the power spectral density. When we compare spectra received independently with both techniques, we see that the new self-homodyne method, here in blue, has a measurement sensitivity that is higher by more than 3 orders of magnitude compared to the former technique. Also, the achieved sensitivity is not yet limited by back action from photon recoil, so it can be still improved by increasing the scattered power. Furthermore, the detection efficiency obtained in the setup with small numerical aperture is very high, about 2.1%, and matches exactly the theory expectation. And finally, the system can already be used to cool the particle's temperature towards a few millikelvin. This is indicated by the decreasing amplitudes of the motional peak in the spectra. So what now? Maybe you've heard that ground state cooling of nanoparticles was already achieved in optical traps. But optical traps suffer from high decoherence due to photon recoil. Paul traps are dark and therefore suitable for further quantum experiments as creating superposition states of a nanosphere. We predict that thanks to the self-homodyne technique, ground state cooling in Paul traps is feasible and offers new possibilities to explore fundamental physics. With this, big thanks to everyone who contributed to this work.